Okay, so starting with number 12, we're just balancing a reaction, right? And we've done that before. So I don't like how little room there is to work on this, so. So I'm gonna go up here and work on it. So C, H, and O. Okay, it's just C, H, and O. How many carbons do we have on the reactant side? Hydrogens and oxygen. Yes, sorry, I started looking up here. And on the product side? 1 carbon, how many hydrogens? How many oxygens? 3. Okay. They all need to be fixed. What do y'all want to start with? I'm going over questions 12 through 15 from last quiz, and then I have a worksheet over thermochemistry. Also, there's a lot of new people on Zoom. That excites me. It makes me so happy. If you go to my website, I'll send it out in the chat. You can pull up the worksheet for today. It's worksheet 7. Okay. Which one do y'all want to fix first? I kind of want to fix oxygen first. Actually, no, I don't know. What do you guys want to do? Carbon? Okay. Let's do carbon. How are you going to fix carbon? Slap a 3 in front of what? Yes. So 3, how many oxygens do we have now? 6. Okay, which one's next? Hydrogen or oxygen? Oxygen, what do you want to do with that one? 3 in front of the O2? 6. And how are we going to fix hydrogen? We need to go from 2 to 8, right? How are we going to do that? 4. So that's at 8. But now what happens? How many oxygens do we have on the product side now? Not 9. How many do we have here? 6, and then 4, 10. Well, how are we going to go about this? 6 and 10. Put a 5 in front of the O2 instead. So then we went from 2 to 10, right? And it's balanced. Everyone on Zoom, does everyone on Zoom get that? Did that work out for y'all? And also, if you ever have a question, you can just send it in the chat, and one of the people in the class will see it and let me know, because I really suck at checking my screen. So now we have it balanced. It's 1, 5, 3, 4. So then number 13, when 2.50 grams of propane, which is the C3H8, are combusted with 7.25 grams of oxygen gas according to the above reaction, what is the limiting reactant? How do we find limiting reactant? Ouch. Right, we need to figure out which reactant is limiting how much product we can make, right? So kind of the weird thing about this is typically in these limiting reactant problems, it'll tell you what product to go to, right? But this one does not. It just says which one limits. So what that means is you can choose either product you want. It doesn't matter. For choosing that? Oh, I see why. Because of question 14. I don't like that that's broken up. Yeah, I do not like that setup because you have to read question 14 before starting to work 13 to know what you need to find. Okay, so reading question 14, which product do we need to find, do we need to use to find limiting reactant? H2O, water. Yeah, wow, I hate that a lot. Okay. That's okay. We're learning together, I guess, apparently. So we're going to use the grams given of each to go to water, right? So we're going to go from, on our mole train, we're going to go from grams to moles, right? So let's start off with propane. We're going to do 2.50 grams of C3H8 goes to how many grams of C3H8? The molar mass. What's the molar mass? Someone calculate that. 3 carbons and 8 hydrogens. I'm going to do 44.1. Does that work for you guys? To keep it at 2 decimal places. And what's going to go on top here? 1 mole of what? C3H8. We're not done yet. What's going to go down here? 1 mole. Where does the 1 come from? From our coefficients. There's an understood 1 right here. So what are we going to go to on top now that we're in the balanced equation? 4H2O based on our coefficients. Oh, shoot. I meant to put mole there. What's one thing that you absolutely have to remember to do or you're going to get points marked off? Cancel your units. And now we're going to math. So how many moles of water did y'all get? Wait, first of all, how many significant figures should our answer have? 3. So with significant figures, how many moles of water can we make from the amount of propane? Yes, 0.227 moles of water. Okay, now we're going to do the exact same thing with oxygen gas. So we have 7.25 grams of O2. How many grams are going to go on the bottom? 32.00, because we have 2 oxygens. And when you look at your periodic table, it says 15.9999. It just keeps going. So she said at some point in the beginning of the semester, just round it up to 16 and use that. So that's what we're doing. And that is equal to 1 mole of O2. What's going to go on bottom? 5 moles from our balanced equation. And we're going to go to 4 moles of H2O again, right? And how many significant figures? 3. So how many moles are we going to make? I got 181 as well. 0.181 moles. So which number is fewer? Which number is smaller? Right, this 0.181 is smaller than 0.227. So that means that oxygen is our limiting reactant, right? And that's your answer, O2 is the limiting reactant. It's just asking which reactant is limiting. Is everyone on Zoom okay with that? Give me like a thumbs up or like a yes in the chat. Okay, cool. So up next, so the reason we had to go to water was because of question 14. I don't like that. What is the theoretical yield of water in grams based on question number 13? What is the theoretical yield? Yeah, so the reason it's called a theoretical yield, basically that number of moles that we just got from the oxygen, we're just going to take that to grams. That's our theoretical yield. It's called theoretical because this is assuming we're in a perfect world where we're not losing any energy to heat. Like our recovery is absolutely perfect. So basically, theoretical because the number that you get is in a very perfect world where you did absolutely everything correctly, which never ever happens. So all we're going to do is we're going to take this 0.181 moles of H2O. We're going to take it into grams. So 1 mole H2O. How many grams of water are in 1 mole? 18.02, and that's from the periodic table. So then we're going to do some math. How many grams of water do we make? First of all, how many significant figures do we need? 3. So how many grams is this? 3.26 grams. That's your theoretical yield. Everything went absolutely perfect in the lab. So number 15 is taking this basically into a laboratory application. So you ran this, you combusted propane in lab, and you only got 2.75 grams of water. That's all you got. So now we need to figure out percent yield. Whenever you see this word percent, what should you start thinking? Part over whole times 100. In this case, what's our part and what's our whole? Actual over theoretical. So this is, sorry, was someone on Zoom saying something and I just cut you off? Okay, cool. So basically this is what I've actually recovered versus what mathematically should be possible. So 2.75 divided by 3.26 times 100. And then you math. Almost. How many significant figures?
3.
Yes, 84.4. So everyone on Zoom, are you guys good with that? Okay, cool. So looking at time and looking at, ooh, that was the answer key. So looking at time and looking at the worksheet of hand, we may not finish it, but that's okay because Wednesday's going to be a test prep. So if we don't finish it, I'll just tack it on. Yes, I'll just tack it on to the front of that worksheet. I don't know yet. Oh my goodness, I need to email and get a room. I'll do that. Well, I guess I'll figure it out tomorrow because they're closed now. Okay, so this is basically like an intro to thermochemistry. I sort of planned on ending this worksheet with Hess's law, but I decided not to because I decided this worksheet was getting a little long. But we'll go over Hess's law next time, I promise. So number one, what is thermal energy even? Yep, it's heat energy. If you had to come up with a definition for it in sort of layman's terms, roughly, what would you say? And by you, I mean anyone. Yes, it is thermal energy, or heat is a form of kinetic energy. So kinetic energy associated, excuse me, associated with movement of atoms or molecules. So I don't know if y'all have ever been, so I guess I'll share sort of like an anecdote to make this make sense. Growing up, my family was like a hockey family, which is weird for Texas, but they really liked hockey. And so my brother played. One year we had to go up to Minnesota, which is absolutely freezing if you've never been. I don't recommend it in the winter at all. But we had to go for a tournament. And I was like really young. I was probably like 8 or something. I was freezing. And my dad told me, oh, just go run laps around the rink. Because it was like outside on like a lake rink. Why did he say to go run laps? Movement warms you up. So the way that I sort of remember this definition is things like running, things like shivering, sort of relate them to things that you have personally experienced. When you shiver, you're moving your muscles, you're generating heat energy. And ultimately, that comes down to the movement of atoms and molecules in your muscles. So shivering is a pretty human example of that. So fast-moving molecules. So we've talked about movement of atoms and molecules. We've talked about it in relation to heat. So will fast-moving molecules have high or low thermal energy? High. What's the mathematic symbol for heat? When we're writing an equation, how do we represent heat? What was that?
Q.
Q. Q. So what is heat? How would you define heat? That's okay. Ooh, sort of. I get what you're saying. It's okay. So our definition for this, heat is the transfer of thermal energy. So one kind of, I guess, difficult concept that, or at least it was difficult for me to wrap my head around when I first heard about it, was that when it comes to hot and cold, there really is no such thing as cold. There's heat and there's absence of heat, right? Which is really weird to think about for me, at least. So think about it. Let's say you just went to Starbucks, you got a hot coffee, and they didn't give you a cup sleeve. So you grab it and you burn your hand. You would say, ow, that's hot, right? But what that really means is that heat transferred from the coffee cup to your hand and it burned you. It was a transfer from hot to cold, right? So if you sort of think about like concentrations, I'm going to talk about this because I know most of us in here are biology-focused majors. When you talk about things like osmosis, movement of water from high solute concentration to low solute concentration, that's what heat is doing. Heat moves from something that's hotter to something that's cooler or doesn't have as much heat. So it's trying to balance out, right? So an exothermic process blanks heat. Does it absorb heat or release heat if it's exothermic? Release. Sorry I made this line so small. So release is X as in exit. It's leaving the system. So that means an endothermic process must absorb heat. Okay, so I put this on here because this isn't exactly it, but I remember very vividly seeing this question on one of my exams when I was in this class. Not this exactly, but very similar. Which is the smallest unit of measurement for energy? Is it a calorie with a lowercase c, a food calorie with an uppercase c, or a kilocalorie, kcal?
Food calorie and kcal are the same, so it's a lowercase c.
Here, what? Yes. A, that is the smallest. Food calorie and a kilocalorie are the same thing. If you ever, pretty much, I feel like America is basically the only country that just says calorie. Typically, if you've ever had like a Mexican soda or something on the back, it's going to say kcal. In most other countries, they're like candy wrappers and stuff. They'll say kcal as well, and that's a food calorie. The blank is the SI unit for heat. What's the SI unit for heat? Or not, that's okay. Yes, it's a joule. And this is represented with an uppercase J. So it measures heat, but it also can be used to describe two other things. What are they? So don't worry, we get into the difference. It's okay. So measures heat. It's gonna measure, if we go up here, what's a word that we use a lot up here? Energy. It's gonna measure heat, it's gonna measure energy. And then we'll see towards the end of this worksheet, it can also be used to describe work. Okay, so there's two concepts that we talk about in this chapter that can get a little confusing because they sound super similar. We talk about heat capacity and then we talk about specific heat capacity. So these next few questions are designed to help you differentiate between them. So if you had to describe heat capacity, what would you say? How would you describe it? So sort of that makes sense. That answer makes sense. So they said amount of heat an object can hold. So heat capacity is the amount of heat absorbed or released with a change of temperature of 1 degree Celsius or 1 Kelvin. So heat capacity, it does make you think amount of heat that an object can hold, but there's just a little caveat to that in this definition. It's the amount of heat a object can hold before it moves up a degree. So the capacity of heat that it can handle within 1 degree before it's going to move up. Does that make sense? Okay. So then number 9, is heat capacity an intensive or extensive property? Extensive. Yes, but we'll get to that. So heat capacity is an extensive property. What does it mean for a property to be extensive? Yes, it depends on how much is present, right? So if you have 1 droplet of water versus an entire pot of water that you're trying to boil, that little droplet's going to boil a lot faster, right? So what's the formula for heat capacity? Yes, but I'm going to change that first symbol, but yes. So Q divided by delta T. What is Q again? Heat, work, or energy, right? And then delta T is change in temperature. Is it the CMAT formula? Yeah, we're going to get there. We're going to get there. I just wanted to include this to show you where part of that comes from. Delta T. Yeah, sorry. I know, I'm sorry. I do draw my deltas like A's, and I really apologize. No, it's something I've noticed. Like the way I start to draw that top part, I draw it like an A. So that's heat capacity. So now let's talk specific heat. So the full term is specific heat capacity, but I feel like that gets confusing, so I just say specific heat. So what is specific heat? It's very similar to heat capacity, but there's just one very small difference. Yes, that is true. There is a list of specific heats. So it's almost the same as heat capacity. So it's the heat required to raise the temperature by 1 degree Celsius or Kelvin, but here's the caveat to this one. It's the heat required to raise the temperature of 1 gram of substance. So the way that I remember this is because the specific heat capacity is a lot more specific than the heat capacity definition, right? Because we're adding one more thing, we're narrowing it down, it's getting more specific. So specific heat, an intensive or extensive property? Intensive. What does that mean? Yes, it is the same regardless of how much there is. And that's because we specify it's only for 1 gram. Whenever we're talking about specific heat, we're only ever talking about the amount that it takes to raise the temperature of 1 gram. What's the formula? It does. It does have an M in it. You're not wrong, but that's the next question. Yes. So this is C equals Q divided by M delta T. Don't memorize this one. Don't memorize this one. Don't. I'm putting that here Because we're going to rearrange it. We're going to rearrange it into the one that she wants you to remember. So we need to rearrange it so that it calculates for heat, right? Heat is up here on top. How would we rearrange it to calculate for heat? Yes. We're going to multiply both sides by this denominator, right? So now we're going to get Q equals Cm delta T. This is what I call the CMAT equation because it looks like CMAT. This is the equation I want you to remember. This is the equation she wants you to remember. M is, that's a good question. We never addressed that. M is mass in grams. Regular mass in grams. So we have Q. Q is heat in joules. We have specific heat. Specific heat, the unit. This is like the weird unit. Okay, are you guys ready for this? Yes. Okay, it's joules per grams Kelvin. Do you guys remember her writing that out? It's a weird one, but it's there. Our M is mass in grams, and our delta T is change in temp. And if you notice the specific heat the specific heat unit, if you go back up to this original equation, it combines all of these, right? You have the joules there, you have the mass, and you have the temperature. Okay, a substance gains thermal energy and therefore Q is negative or positive? It's gaining thermal energy.
Positive.
Positive. Okay, so now, I'm sorry, I should have put 14 right after 12. Okay, the specific heat of water is 4.184 joules per grams Kelvin. A bottle with 630, let me restart, guys. I'm sorry, I've been talking way too much today. The specific heat of water is 4.184 joules per grams Kelvin. A bottle with 6,384 grams of water is heated from 50 degrees Celsius to 106 degrees Celsius. How much heat is absorbed? What equation are we going to use? Yes, so we're going to use CMAT. So we're trying to find heat, right, which is Q. What's our specific heat? 4.184 joules per grams Kelvin. I'm going to do something weird with the units, okay? I'm going to warn you guys. I'm doing something weird because I want you guys to see how they cancel out. You do not, oh, I'm sorry, I didn't realize I had to push this up. You do not have to write them like this. I'm just doing this as a visual. What's our mass? (6,384 grams), and I'm putting it over 1. That's weird. I'm just putting the 1 there as a placeholder in the denominator so that I can show you visually how the units cancel out and you end up with just joules. What's the change in temperature? (56 Kelvin). So the number one thing students do here that causes them to lose time on their exam is they try and convert from Celsius to Kelvin. Why don't you have to do that? Exactly. Because this is going to be Kelvin, this is Celsius, this is Fahrenheit. Kelvin, these are the increments, and for Celsius, the increments are going to be exactly the same, whereas Fahrenheit is much smaller. There was a really nice picture on a slideshow that explain this a lot better than that does. But that's why you don't have to convert. So now you just do math. You multiply this all together. And this is how the units cancel. What's on bottom cancels what's on top. And then you end up with joules over 1, which is just joules. And that's why I did that. How many significant figures? It's a big number. Don't worry.
4.
We're going to use 2 significant figures. I know this is confusing. So we're using 2 because of this 56 here.
Okay.
And no. Wait, how many? 15,000?
Or whatever that big number is. 15000.
I did not get that. It is a big number.
15 million.
Oh, what the heck? Why did this happen to me? You're right.
0.5 million.
You are right. I don't know what I did wrong when I was making my answer key. So the answer is 1.5 times 10 to the 6th joules. I just put this in scientific notation. How does everyone feel about that? Yes, that's a good question. If the question asked for how much heat is absorbed in kilojoules, you would divide this number by 1,000 to get to kilojoules because there are 1,000 joules in 1 kilojoule. And you will definitely have to convert between joules and kilojoules in this section, for sure. You know what? I think we're actually going to finish the worksheet. Wow. So you're tracking the temperature of a reaction in a calorimeter. The thermometer begins at 27 degrees, not degrees. The thermometer begins at 27 Kelvin, goes down to 18 Kelvin. Is the system endothermic or exothermic?
Exothermic.
Endo. It's endothermic, and I will go through this. That's okay. So remember when we're in a calorimeter, this is my bad calorimeter, we have a system and then we have surroundings right out here. So when you have that thermometer in there, you're really measuring the temperature of the surroundings. So if the surroundings are, how do I want to word this? If the surroundings are losing heat, then what must be gaining heat?
The system.
The system, right? And a system that pulls in heat from outside feels cold to the touch, right? So if you grab a super cold drink, it feels cold because it's pulling heat from your hand into that cup. And that's why it's endothermic. Does that make sense on Zoom? I forgot, I haven't checked in with you guys in a minute. Give me like a yes, give me a thumbs up, give me an I don't totally get that, I need help. Okay. Then I will charge on. Okay, last 2 questions, I promise. So, what is the formula for change in internal energy?
Delta U Q plus W.
Yes, so you can use delta U or you can use delta E, whichever you're most comfortable with. I prefer delta E because, I don't know, delta U just looks a little ugly to me. Q plus W. What is Q? Heat. What is W?
However much you're gaining.
What does W represent? The word starts with a W. I'll give you. Work, yes. Work. So here we have energy, we have heat, and we have work. So I want to go back to this, number 7. The joule is the SI unit for heat, energy, and work. Everything you do in this equation should be in joules or kilojoules. So a system releases 43 kilojoules of heat, and 80 kilojoules of heat is done. Oh my goodness, that should be work. Sorry. A system releases 43 kilojoules of heat, and 80 kilojoules of work is done on the system. So if we're releasing heat, is that positive or negative value? Yes, negative. Negative 43 kilojoules because we're releasing. If work is done on a system, is that positive or negative? Positive. If work is being done by a system, it's negative. So we're looking for delta E or delta U, whichever you want. Negative 43 kilojoules plus 80 kilojoules. What is our change in internal energy in kilojoules?
37.
Yes, positive 37 kilojoules. What if I wanted that in joules? What would you do? Multiply by 1,000 and you'd get 37,000? 3,700,000? Which one? 100 or 1,000? 37,000, right, yeah. Okay, are there any questions? Okay, Wednesday we'll go over Hess's law, and then whatever else she goes over for chapter 5. And that'll be our test prep. It's Wednesday at 5, and I'll get you room confirmation as soon as I get one. Anyone on Zoom have any questions, lingering questions? Okay, then I will see y'all tomorrow in class or on Zoom, hopefully. Okay, y'all have a good one.